Okay, good. And then let's take it away, and we'll hear your talk. And I think this session is meant to be a relatively informal type of talk, so people are invited to ask questions as it comes along, and we have a mixture of people of various levels of experience, including
Yeah, I
undergrads.
encourage people to interrupt me at any point if they have a question. So I guess I'll start now. So hello, everyone.
Please.
My name is Conor Omand. I'm a PhD student at the University of Tokyo. And today I'm going to be talking about my work over the past 4 or 5 years on multi-wavelength signals from pulsar-driven supernovae. So just some quick background. As most of you all know, the supernova is a luminous explosion caused by the death of a massive star. The shock produced from the bounce of the ejecta on the core is re-energized by a neutrino emission. And so this is the supernova shock wave. The luminosity of a supernova is mostly due to the decay of nickel-56 that's produced in the explosion. Usually their core collapse supernova will have about 0.1 solar masses or so of nickel produced. And so both of these are energy deposition mechanisms, neutrinos and nickel. They can deposit a certain amount of energy, but observationally we see supernovae that are much more energetic than these methods should be able to allow. So there must be some other kind of energy source. And so this is where the pulsar-driven aspect comes in. I just want to quickly say what a pulsar wind nebula is. So the pulsar spin down generates lots of energetic particles. This is where most of the energy from the spin down goes into. This confined wind produces what's called the termination shock, and this can accelerate particles to very, very high energies. And then these particles will emit broadband radiation as well as synchrotron, and they can also inverse compensate scatter photons to up to gamma ray energies. So you can have everything from radio to gamma rays produced by pulsar nebula. They're very, very broadband objects. So what is a superluminous supernova is, this is the main focus, the main observational focus of my work. These are about 10 to 100 times brighter than typical supernova. And these are too powerful to be made by conventional nickel-56 decay. Unless you have tens of solar masses of nickel, which is unfeasible in a lot of scenarios. They're classified, like most supernovae, by the presence or lack of hydrogen. Hydrogen-free supernova are called supernova 1, type 1, whereas type 2 is hydrogen-rich. I'm going to be focusing this presentation on type 1, and I'll explain why on the next slide. The event rate of these superluminous supernovae is about 0.01 to 0.1% of regular core collapse supernovae. And they're usually found in dwarf star-forming galaxies. And these are the same kind that a lot of long gamma ray bursts have been found in. And so a lot of people have suggested there could be a connection between these two types of objects. So there are a few different models for type 1 superluminous supernovae. The collision of ejecta with circumstellar material. This is a model used for most type 2. And it fits quite well, but the light curves don't fit a lot of type 1 superluminous supernovae, although there's the occasional one where circumstellar interaction, well, the ejecta and a hydrogen-free circumstellar material does fit quite well. Another model is pair instability or pulsational pair instability. So these are extremely massive stars that can produce 40, 50 solar masses of nickel or more. And so they can be extremely bright. They leave no remnant though, so there's very little broadband radiation expected after. And the models don't fit the data quite as well. Another one is fallback accretion onto a black hole or neutron star. This one has quite a few parameters. It's also related to GRBs. I have your GRB-like jet as well. And then the last one is that people have suggested is the spin down of a rapidly rotating magnetar. So this is the pulsar-driven model. This is what I study. And so this model can possibly produce quite a few different types of transients. So you can see here if you have an extremely high magnetic field and spin period less than a few milliseconds, you might be able to produce GRB or GRB supernova or hypernova. But if you go lower, the spin down time increases from order of a few minutes to order of a few weeks. And so you can get a superluminous supernovae. And also, people who have been studying FRBs and suggested that these objects, their progenitors might be neutron stars, usually place their parameters somewhere in this region of about 1 millisecond and 10 to the 13, 10 to the 14 Gauss magnetic fields. And then as you increase the spin period above, say, 10 milliseconds, the rotational energy of the pulsar becomes lower than the traditional explosion energy of 10 to the 51 ergs. And so you can get these ordinary supernova, but of course you'll still have a magnetar or pulsar in the center of them. And
sorry, I'm curious, how did this data come by? Like, was it by simulation or theoretical calculations?
this figure right here?
Yes, yes.
This is the result of a few studies. And again, I've put question marks next to everything because we don't know any of this for sure. But these are, and people who have suggested magnetars as the progenitors for some GRBs, probably not all of them, put them in this 10 to the 15-ish Gauss magnetic fields, whereas the superluminous are usually less.
Just to see if I follow, so the bottom right one looks like an image that I have in my office, and the other three are artists' artists' images. Is that right?
I think this one is real data. These two might be artist images. I remember taking these off Google to kind of illustrate a point, so I don't expect that they actually look like this.
Yes, the lower right is the crab. I have that hanging in my office.
These all look like artist impressions. I guess we haven't really seen a superluminous supernova close enough to actually get, resolved data yet, so they would have to be. And so how can we test for a pulsar at the center of these supernovae? Well, we can try and directly detect the pulsar in nebula. We can do this at high energy with the X-rays and gamma rays, or at low energy with radio and millimeter studies. X-rays and gamma rays, there have been a few studies so far. There was a nice one a couple of years ago, people who use Fermi data, and they put limits on a lot of those supernovae. Luminous supernovae. But there hasn't been a lot of radio millimeter studies, or at least there wasn't when I started working on this. There have been quite a few in the past years, and a few years I'll be talking about those. The next method is indirect detection via dust re-emission. And this we expect to be in the infrared. And then you can maybe see some interesting forbidden ionization lines in the optical, as well as you can see some interesting polarization signals if your engine significantly distorts the supernova geometry. So if it's not spherical, you can probe that with polarization. So what I've been working on so far is these radio millimeter studies and this infrared stuff. I haven't worked so much on the optical or polarization yet. I'll talk about this a little bit at the end, but this talk will be focused on these two tests. So the detection, or the radio and millimeter model is like this. So at the very beginning, the ejecta is optically thick in every band. And so all of the pulsar and nebula emission is thermalized in the ejecta and re-emits. And this is how you power the superluminous supernova. And then after some time, which depends on the frequency of the radiation, you can start to have this, the pulsar and nebula emission leak through. And so what we want to do is we want to find what this time scale is, and is there enough emission leaking through to be detectable. And so how we went about this is we first fit the early optical emission. We fit this with a 3-parameter model: the pulsar spin period, the ejecta mass, and the magnetic field of the pulsar. And so you can see here we fit 6 different supernovae. We only fit near the peak because our model was quite simple, and we were able to get some parameter sets here. Unfortunately, there is a degeneracy because we're essentially just fitting the width, or what's it called? The width of the supernova and the peak luminosity. So 3 parameters, and fitting 2 things. And so what we did was we first fixed the period at 1 millisecond. We call this the minimum spin period because we expect that anything rotating faster than that will be at the mass shedding limit. And we would slowly increase the period and adjust the other parameters until we found that the light curve shape just didn't fit anymore. And you can see this on the right side here. The purple one is the 1 millisecond. So this is the P-min model. And you can see it goes through all of the data near the peak quite nicely. And we go all the way up to 2.3, 2.4, and we see it still fits nicely. But once we get to 2.5, we see that the light curve has this little kink in it, and it becomes very, very thin. And so there's no way, at least that I found, to be able to fit the light curve with a 2.5 millisecond rotating pulsar. And so we say this is the P max. And so this was 2012 IL. You can see P max here is 2.4. These are the parameters that we found. The ejecta masses are usually between 5 and 15 for P min, but go down. They all decrease to less than 5 at P max. And you can see the magnetic field here is also decreasing as well. And the P maxes are usually somewhere in between 2 or 1.5 and 2. We have this outlier with 4, but they're still not rotating slowly. But
so sorry, I have a question.
Yep.
So this light curve, is it representing the entire energy coming from the essence? So both the contribution from the pulsar wind, the nebula, and the contribution from the circumstellar material around. I mean, I want to understand the things that are forming this light curve.
So this light curve, the power, we have a 10 to the 51 erg explosion. We just fixed that. And then the rest of the luminosity is completely because of the pulsar. We assume no circumstellar interaction for this model. We wanted to keep it fairly simple.
Okay, so I'm just wondering, how do you disentangle the energy from there's a kinetic energy from the ejector and the pulsar, the one from the pulsar? Is that
right? So we have I think the assumption that we make, and again, this is it's an assumption, is about half of the pulsar energy goes into kinetic energy and half of it goes into thermal. And about the same is done from the initial explosion energy. Half of it's kinetic, half of it's thermal.
Okay. You also talked about the time scale for which you like the pulsar wind nebula becomes dominant. You said like 1 year after the explosion or something like that.
Right. So there's something called the spin down time of the pulsar, and this is when this is the time scale at which the pulsar emits most of its energy. And so the spin down time scale for 1 millisecond pulsar with, say, 10 to the 14 Gauss magnetic field is on the order of a few days to a week.
Right. So this is just within that time frame.
Yeah. So the pulsar nebula tends to dominate after the spin down time, as long as the spin period is less than about 4 or 5 milliseconds.
Right. Thanks.
Yeah, no problem.
And just to see if I follow the models, you adjust the parameters you are adjusting. So you measure basically the total energy and the rate of change and the decay of the energy coming out of your supernova. And that you match by saying that energy comes from spin down of a pulsar. So obviously it's it's omega times omega dot. It's actually omega squared times omega dot times some inertia moment, which is constant. And then the omega dot you map onto a B13, right?
Yes.
And that's why, in order to, if you have a slower rotation, a slower Pmax, you need a bigger field to get the same energy out. Since at the end of the day, you're normalizing to the total energy you see. Now, as you decrease the as you decrease the period, I'm just trying to see which way it goes, as you decrease the kinetic energy of the neutron star, you get the same energy out by making it spin down faster, which is why you've got a bigger field for the longer periods.
Yes.
However, I guess when you're fitting the data, at the same time, of course, the spin down time also changes, which is why, and it looks like the way it's going in your models is that at one equals p squared. So at the longer period, if you make the period too long, what you'll find is that the spin down time is too long, I guess, according to this plot.
Right.
To fit the data, and if the spin, so in this case, if spin down time becomes longer than a week, whatever you're trying to fit for here.
Well, the other thing is that as we increase the spin period and decrease the magnetic field, in order to fit, we have to decrease the ejecta mass. And so you can see here that this is one solar mass of ejecta. This is a very stripped star. And so you start to see there's just not enough diffusion in the ejecta. So you start to see more of the like an ultra stripped supernova essentially.
Does that actually affect the energetics?
It definitely affects the shape.
It does.
Yeah, because here, like, we would have to have ejecta mass of less than one solar mass, for example, in order to try and fit this.
So is that a hard constraint you put in there, that ejecta mass has to be at least one?
It's not. It's just what we found from fitting, or what I found from fitting.
Okay. Okay, thanks.
And so, yeah, this is how we get our parameters, and then we can calculate a broadband spectrum. And so you can see that on the low energy side, as we go down, this is the free absorption cutoff, and the dashed one here is if we assume the ejecta is completely unionized, so there is no free absorption, this is synchrotron self-absorption cutoff. But you can see that these cutoffs move lower and lower in frequency, and so you'd expect that, for 100 gigahertz, we should be able to see it quite brightly here, but 1 gigahertz, nothing yet. And then 1 gigahertz emerges on a time scale of 10 years or so. And when we plot some light curves, this is the intrinsic one for one of our supernovae. We can see that again, at 1 year, we start to see the 100 gigahertz emission. So this is an ALMA band, and it gets to extremely bright luminosities. And we start to see the 1 gigahertz emission around 10 years. And it never reaches the luminosity that the 100 gigahertz did, because the Pulsar nebula has been decaying in energy.
And that's the thermal emission you're plotting here.
This is synchrotron emission.
To get synchrotron, you would need to know the relativistic population and magnetic fields and all that. How do you predict that?
Yeah, so we do a full Boltzmann equation solving. So it's kind of complicated, but we have we include pair cascades. We include we have the electron injection from the Pulsar nebula, which we assume is crab-like. Which again may be a terrible assumption. We don't know, but that's what we're calibrating on. Yeah.
Just curious, where does is this a model that's a public code, or is it something that you guys developed?
This is something that my collaborator developed a couple years before I started my PhD. So I can send you the references if you're really interested. The lead author on those papers is Kota Murase. And he developed them in 2015, 2016, the papers are.
Okay, great, thanks.
So let's look at the 1 gigahertz emission, taking into account, how far away taking into account, say, redshift and how far away the supernovae are. So you can see the absorbed and unabsorbed in solid and dashed here. For 1 millisecond P min, we see that a couple of them are not bright enough to ever be at our detection limit here, but a few of them are, again, time scale of 10 years. This was the persistent source emission from FRB 121102. We expect that if it was a pulsar that we could maybe see something similar in our models. And the Pmax curves you can see, excuse me, all of them except this yellow one, which was quite far away, should be detectable, timescale of 10 or so years. And this red one, Supernova 2015 BN, it gets extremely bright and decays over an extremely long time scale. So this could be something we could see for 100 years or so, if our model is correct. And we can get similar fluxes to what we saw from the FRB persistent source.
Just to see, so since you got this line for the FRB 121102, so you speculate it's possible that the 121102 is in fact such a spinning down magnetar, let's say a decade or two, a few decades afterwards. Is there any data from 20 years ago of whether there was a supernova there?
No one's, people have looked through it and no one's seen it. So it could, I mean, the timescale that we're looking at it could be up to 100 years old. And so we just might not have data going back that far, but people have looked for it, no one's seen it.
Right, obviously 100 years ago, people didn't look very systematically.
Yeah, yeah. So let's look at the 100 gigahertz emission now. You can see again, the time scale becomes close to 1 year and 1 millisecond. You can see that there are 4 of them that are detectable. One of them is extremely bright. This is again 2015 BN. And for Pmax, we predict all of them are detectable on a time scale of like 1 to 2 years or so. 15 BN should be detectable for another 30 years. So this looks like an promising method of detection for some of these supernovae. This is a now 5-year-old supernova, so we should be able to see it quite brightly. And so these are some of the supernovae that we went ahead and did observations of. So I'll start with the VLA targets. You can see 10 targets. Here we observed at 3 gigahertz. A couple of these already had late time radial limits, and we got beaten to the punch on one of these by another group who detected this PTF10 HDI at 6 gigahertz. This is a 7-year-old supernovae. And so we did observations of these 10. We got noise, 1 sigma noise levels of around 10 microjansky. So this would be on the same level as what I showed in the last slides. And we too also got a detection of PTF10 and HDI at 47 microjansky. So I'm going to show that data here. This is a 3.3 sigma signal. Some people don't even want to call it a detection because of that number, but we can see that it's completely spatially coincident with this white box, which was the detection from the other team at 6 gigahertz. You can see the models that I used, the Pmin, Pmax models. And so for 6 gigahertz, you can see that the Pmax models overestimate the flux by a lot. Whereas at 3 gigahertz, they only slightly overestimate. So we know that this isn't a maximally spinning pulsar. It doesn't matter what the absorption is. But it is consistent with, or in between the minimum and maximum absorption for Pmin. And so what I did was I tweaked the ionization state of the ejecta and found that if about half of it is unionized and half of it is singly ionized, that we can actually fit both data points. So this is the model that we went with for this paper. Time will tell if this is an accurate representation of what the pulsar actually is. And for the rest of the sources, we didn't get any detections. And so I'm just going to explain what this table is. You can see for Supernova 2005 AP, our lower limit is below all of our model predictions. So all of the models we have are excluded. So you can see for AP here, all of them are excluded. For 2007 BI, only our unabsorbed models are excluded, whereas our absorbed models, we shouldn't have been able to see it yet. And so you can see for BI, the unabsorbed models are excluded. All the rest of them are considered still viable. So this is again how you read that table based on these kinds of plots. And so you can see here that most of the unabsorbed models are completely excluded, except for a couple. P maximum models have been excluded for 4 of them. So we were able to actually constrain the pulsar in these studies. And if we assume that all of them had PTF 10 HTI like absorption, so 50% ionized, we were able to exclude 3 of the 3 of the 9 supernova that we looked at. But we were only able to completely exclude 1 of them based on our observations. And for in the millimeter in ALMA, we looked at 3 supernovae, 2015 BN, this bright red one that I showed earlier, 16 ARD and 17 EGM. These are both extremely bright. And so you can see our predictions for 2015 BN. We should be able to see it at a level of 200, 300 microjansky, which is extremely bright. ARD not quite as bright, but we should still be able to see it at 2030. EGM was also expected to be above 100 microjansky. But when we did our observations, we found that for 2015 BN at 100 and 230 gigahertz, this is red and blue. Both of these are non-detections below what we thought should have happened. The green and purple here are for ARD. Again, both of them were non-detections below our model lower limit. EGM was also below our model lower limit. So all of our millimeter predictions failed. And so we don't really know what this means yet, but there was another group that had done quite a few observations. And so you can see them all here. I know it's a little bit small, so I apologize. But they did some VLA observations and some ALMA observations. And their sample size was about 30, so much larger than what we were able to do. And they got about 5 of them. Like this one here, the light blue one is under the model prediction here, light blue is under model prediction and yellow. Here, light blue is under, here, light blue is under. And so about 5 or 6 of them where they predicted a detection, but they did not get one. So the only, this is Eftikari, this is the same group that detected PTF10 HEI in the first place, but the rest of, nothing else from the sample they were able to detect, and about 5 of them they should have seen, regardless of model. So this is troubling for the pulsar-driven model, at least as with the parameters that we have kind of assumed. So we really need to look at that. I want to talk about this new PTF10 HEI data. So this is the original paper that I was talking about before. This is the Eftikari paper, the original detection. And this is new data that just came out in August. They were able to detect it at 1.2, 3, 6, and 15 gigahertz. And it was still quite bright in all bands. And so these are 2 models. This is the model that we used in the previous paper. So this is P min with, well, I show minimum and maximum absorption here. And you can see that the blue one, the dark blue 6 gigahertz, again, our minimum absorption model works somewhat well. Black minimum absorption is close, red minimum absorption is close, but light blue, the 15 gigahertz, we vastly underpredict the data.
Just practically, so when you see a radio source in the right location, how do you know it's actually the supernova and not some other radio source nearby in the same galaxy?
There's a few different possibilities. It could be like radio loud AGN. It could be an off-axis jet. It could be something from an external shock. So like we did a lot of these tests. We looked at like these, well, for PTF10 HEI, we looked at spectral indices, and we found that it really didn't match up with off-axis jet. And then there are some arguments, mostly in this, the first detection paper, this Eftikari one. They argued about that it could not be an AGN based on some kind of statistical arguments, that it just didn't fit the type of host galaxy. I forget what other, they talked about obscured star formation, but they said it was not consistent with that either. So A lot of their arguments originally going to the Pulsar Nebula. Like it was most consistent with that.
I guess you'd have to wait another 10 years to actually watch the time rate of change.
Yeah. Well, even the 2-year one here, I expected some level of change at the, and we can see a little bit of rise in the 3 gigahertz emission. It seems to look it's going up a little bit. So there is some time variance even over a scale of 2 years. But this model, again, underpredicts greatly. So our model essentially rises too early, so it has time to decay down. Whereas the other one from this new paper that's coming out uses a model which is closer to a P-max model. So much lower ejecta mass, much higher spin period. And they have the exact opposite problem. So their model is, or I guess it's still our model because I'm on this paper, but at 15 gigahertz it's pretty close. 3 gigahertz is roughly consistent with the unabsorbed model. 3 gigahertz, it's consistent with some level of absorption, although it seems to be changing. But this black curve here, or black data point at 1.2 gigahertz, you can see that it rises much, much later than the timescale that we've been looking at. And it, again, vastly underpredicting. So the P-min model seems to rise too early, and the P-max model seems to rise too late.
Has there been any attempt to search for pulsations?
I don't think so. Well, you mean like fast radio burst pulsation, or what kind of pulsation?
Well, I'm just thinking of SGR 1935 plus 20 is known to give out mega-Jansky pulses. So
yeah.
if those might be visible at that kind of distance.
Yeah, we did. So I know our study and this other study did like the time resolution was about 5 milliseconds. So we could have seen a fast radio burst.
Did you search?
Yeah, we looked for it. We didn't see anything. And we looked for them in all of the samples we took, and we never saw any fast radio bursts. And after this new paper that's still in prep, again, did the same analysis. I think the time resolution is the same, 5 milliseconds.
So did you do this by running a pulsar search mode beam at the same time as imaging?
I don't know. I don't know exactly how the pipeline works. It was developed by Casey Law. It is commensurate with the VLA, like all the VLA data is essentially cloned and sent through this pipeline.
So it's a real fast pipeline.
Yeah, it's real fast. Yeah. Okay, good. You know how it works, so I don't have to try and explain it.
Yes, of course. In these cases, for all the candidates, you know the position perfectly. I mean, better than the resolution of the telescope, right? I mean, all these supernovas are known to an arc second at least.
Yes, yes. And so a few of them we like. One of these other ones, PTF 12 DAM. This one here, you can see there's a lower limit here, and not just one of these, because there was a signal detected that's consistent with the optical emission from the galaxy. And it traces the center of the galaxy. So it looks like it's some kind of star forming region. But we're able to say that it's not the supernova because it's not coincident with the position.
Just give us your sample of supernova, super luminous supernova. Is that a complete inventory of everything that's known that you went after, or just some special ones you selected for suitability?
So in this particular study, as far as I know, again, I joined this group after they selected their samples, so I wasn't a part of the selection, but I believe it's volume limited as of 2017 or 2018 to something like redshift of 0.35. So it should be everything close.
Good. So there, how many? There are 24 of them?
This is 29, but this is median values. There are also some where we couldn't get a good fit for the parameters. So there are other data points here that we don't have in the figure. So I think the sample size is over 30.
And just curious, how complete is the sample or sky? I mean, these come from various surveys, Ogle and PTF, that look in particular places. So there probably are more out there that just weren't looked at. Is that right?
Yeah, I would guess so. I don't know what the completeness of the sky surveys are right now. I'm sure LSST will increase that number by quite a bit, or the VRC Rubin Observatory.
Yes, great.
Yeah, so unfortunately, I can't say exactly how many luminous supernova there were, or even really give an estimate, because I don't know the completeness of the surveys. Anyways. Okay, let's kind of summarize this first part of the talk. So we observed roughly 30 targets in radio and millimeter over the course of 3 papers. We got 1 detection on PTF10 HGI. This is mostly consistent with the model, but the parameters we don't know yet. It's not consistent with the Pmin or Pmax. It might be something in between. We haven't really done a full parameter study yet, but it's most consistent with the Pulsar Nebula as opposed to AGN, off-axis jet, anything else really. And the rest of them were undetected, but we should have seen a few based on these models. About 6 or so, maybe even more, 8 or 9 we should have seen. And so these non-detections suggest that there's some kind of problem with the model that we're using. Either these supernovae are not pulsar driven, which is obvious. We're just completely wrong, but that's kind of the last resort, so we don't want to go there quite yet. The ejecta could be more heavily ionized than what we predict, and so therefore there's more absorption. There has been a study using a code called Cloudy that said our assumed singly ionized oxygen is roughly correct at most timescales, or at least it's a conservative estimate. So I don't think it's a matter of absorption. But what I think is that the electron injection spectrum is not crab-like. So the crab is has a very flat injection spectrum. So there's a lot injected over all energies. And so what might be going on is that all the injection is taking place at high energies, and we just don't get a lot of low energy emission. But then this begs the question, could we see this, why haven't we seen these in X-rays or gamma rays, where there could be a lot of emissions? So there's still the question of where is the energy going, and we don't know that yet. There's still a lot of work on, what kind of injection spectrum could we have? So, any questions on radio millimeter before I move on? Okay, let's go to dust then. So, why do we care about dust in these superluminous supernovae? Well, it can absorb the UV optical emission from the Pulsar nebula and then heat up and emit an infrared. And so we want to determine which of these supernovae form dust at all. How do the different pulsar parameters affect things like the formation timescale and dust size? And is this actually a feasible method of detection? And so what we did, we calculated the ejecta dynamics. This is using the same code as before. We calculated the dust formation and growth using a model from Nozawa and Kozasa. We calculated the dust temperature, and we accounted for sublimation. So this is when the optical emission is just a little bit too bright and it breaks apart the dust as it's formed. We account for ionization. So if the gas is ionized, it's going to be much harder to form dust, and we think it probably won't form at all. And then we calculate the blackbody emission from the dust if it forms. So this is the model we have. We have the neutron star pulsar nebula at the center, and then we have the ejecta, which I've sectioned off into 3 zones. This inner zone we call the ionization and sublimation region. So this is where the gas is either ionized and cannot form dust, or as soon as it does form dust, it's sublimated from the pulsar nebula emission. And so this is a dust-free region. Once we get to past the sublimation radius or the ionization radius, we have this thin absorption region. And so this is where all the optical emission is absorbed. We assume 100% absorption just because it's a 1D model. And then it's re-emitted by the dust. And so this thickness is the optical UV emission is roughly equal to 1, or optical depth roughly equal to 1. And then the outside here, nothing is absorbed by the dust because nothing's really getting through apart from maybe radio emission. And so the IR optical depth is much less than 1. All you need to know. We studied 2 different compositions. We called them 1B and 1C because of what supernova they're supposed to resemble. We look only at carbon, oxygen, magnesium, and then silicon for this study because all the primary dust that's formed in each supernova we expect to be either carbon or silicate, magnesium silicate, or magnesium oxide, depending on the composition. Silicon for the 1B or the 1C composition is not 0. We expect it to be about 10 times less than the magnesium. But because we expect that magnesium oxide will dominate here, we just don't track the silicon. So this is why it's 0. And we look at 5 different kind of ID parameter sets, few in the 1B, 1C composition with 5 and 10 ejecta mass, solar masses of ejecta. And here this epsilon E is essentially a multiplicative factor on the Pulsar nebula. So this just cuts all the Pulsar nebula emission in half. And we just wanted to see what happens with, with that. So how does a pulsar affect dust formation? Well, the big thing is it delays it. So you can see based on the x-axis here, this red curve is the dust nucleation rate. So as this spikes up, dust starts to form. And this green one here is the concentration fraction. So it's the fraction of gas molecules that are locked up in dust. So as this approaches 1, it means that the gas or the ejecta will be essentially completely dust. And so we don't really have anything else going on in our model, like carbon monoxide formation. And so all of the dust grains eventually get locked up in dust. This is the size down here, and the purple one you don't need to worry about. And for the pulsar, for the one with the pulsar, you can see that the nucleation rate spikes up and keeps going even when it should be forming dust. This is because it's getting sublimated as it's formed. So we're getting this kind of equilibrium between the minimum dust size that our model can look at and the kind of minimum dust size and maximum, I guess, like pre-grain size. I'm not sure what exactly to call it. And you can see that this actually dramatically lowers the size of the dust as well. And dramatically increases the time scale.
What's the coupling there? So it's the gamma radiation from the pulsar that dissociates it, or what should from the pulsar wind nebula that affects it?
It's the pulsar nebula emission. So this is from sublimation. So it's,
but I should be thinking of the dust far on the outside, right? So this is past any of the wind nebula. The dust would normally, obviously, there are 2 things. In the nebula, it's in the pulsar wind nebula. Obviously, everything is just hot and shocked.
Yeah,
and
yeah. This is all in the ejecta.
But this is outside, in the ejecta, outside the pulsar wind shock region. And there, you just get the radiation from the pulsar wind nebula dissociating, and that would be primarily UV radiation, I guess, that's doing it?
Yeah. The band that we say is 2 to 6 EV. It depends on the dust size as well. So there's a lot of assumptions going on here. Yeah, UV. Yeah. So these are the effects of pulsars. Let's look at the effects of different pulsars and how they affect the sublimation radius and ionization radius. So we'll start with 10 milliseconds here, and you can see that the green one here is the ionization radius. So it's quite, there's not that much as ionized, and the sublimation radius is below the inner edge of the ejecta, if we assume a thin shell. So we expect for a 10 millisecond pulsar that this will form dust without any problems. For this one here, you can see that originally the sublimation radius is outside the outer edge of the ejecta, and so we don't immediately form dust. And there's this time scale here where the emission goes, or the sublimation radius goes inside the outer edge, and the ionization radius will keep pushing out is not at the outer edge yet. And so here we expect some carbon dust to form. And here we might have a little bit of magnesium silicon oxide that forms, but it seems like most of the gas will be ionized before that, before we would start to form dust here. So we expect only carbon grain growth here. And in this one with a 1 millisecond pulsar, you can see that the ionization radius it just hits the outer edge of the ejecta almost immediately. And so we never expect to see dust in this kind of system. So let's look at the formation timescale. Unfortunately, I couldn't self-consistently calculate the ionization effect. So the color map here does not include ionization whatsoever, but I've included the region where we expect dust to never form is this solid region here because of ionization. And so this is mostly, extremely fast rotating pulsars, less than 2 milliseconds, and magnetic fields of about 10 to 12 to a little bit less than 10 to the 14 Gauss. So the normal timescale for carbon dust growth is about 6 months to a year. The maximum timescale, which is down here, which again will never form but is not calculated there, it's roughly 3 years or so. So this here would be something like 500 days based on the, or maybe a little bit more because of the color. But what's interesting is up here, for an extremely high magnetic field pulsar, we actually see that the timescale is reduced. We form dust sooner. And this is because the pulsar spins down very quickly and it injects all its energy very quickly. And so the ejecta becomes very, very fast, and adiabatic cooling becomes very, it becomes a good method of cooling the ejecta. And so we start to form dust at extremely short timescales. For different types of dust, we see that this timescale is increased. This is, a few more, a bit longer. I know I'm running out of time, so I'm going to start moving a bit faster. So yeah, for these extremely high magnetic field pulsars, we should be able to see some dust formation, but not for this kind of lower 10 to 12, 10 to 13-ish. Dust size is decreased by pulsars even in this kind of fast formation timescale because the ejecta is not very dense when it's being accelerated so quickly. And you can see that this looks like it's all the same size, and this is because this is the minimum size that our sample can, our minimum size that our model can look at. And so you can see the minimum size here is essentially the same for everything in carbon because it's at our model minimum. And so it looks like we would be in the equilibrium of dust formation and sublimation for an extremely long time. We may form dust, but it will be very, very small if we do. And this is over an extremely, extremely large portion of the parameter space. And so if we can form this dust, how much we'll emit is detectable. So for this is kind of close to a P-min, like generic P-min, 10 to 14 Gauss, 15 solar masses in 1 millisecond. We can see about new is about 10 to the 38 ergs. 2 years, 5 years, and 10 years, it's in these shaded regions. This shaded regions is because the uncertainty in the pulsar nebula spectrum that I talked about. This is kind of the upper limits. This is a very crab-like pulsar nebula spectrum, whereas this is a kind of a minimum if you expect that, this is just purely set by relic electrons. And you can see in this other one, it's brighter, but again, we're still in the shaded region at all times. So is this a viable method of detection? Well, it really, really depends on the spectrum of the pulsar nebula, whether the dust emission will dominate over it or not. So this is still something we need to look into. This is something we're trying to constrain with our radio observations. Ideally, we would be able to do these things in tandem, like do sub-millimeter observations, get some handle on the pulsar nebula spectrum, and then we can look at dust after that. So this is the summary of the infrared. We calculated dust formation for multiple ejecta compositions and pulsar parameters. Formation timescale can be accelerated to about 50 days with a kind of GRB supernovae. or it can be slowed down to order of 10 years or 10, 20 years, or it can be completely completely stop ionization. The dust size we find can be reduced by about a factor of 10 because of a pulsar, and it goes all the way down to our model minimum, so it might even be further than that. And the emission is detectable out to about maybe a gigaparsec with very, very favorable parameters if you looked at with JWST, but it depends heavily on the spectral index of the pulsar. So this is the summary of basically everything that I've been doing. I just wanted to talk about the two kind of optical things that I brought up earlier. The first one is nebular spectroscopy. So recent observations of supernova 2012 AU, kind of sub-superluminous supernova, if I can say that. So not quite superluminous, but much more luminous than usual. They found a forbidden ionization line, oxygen 3, at a timescale of 6 years post-explosion. And you can see the same forbidden line is at a timescale for the superluminous supernova. It's present at a timescale of about a year. But this oxygen line that's found in all these other supernovae, like these are 1C supernova, and you don't see this forbidden line here. This is the same supernova, but at 1 year. But this oxygen line is completely gone. And so what they said is this is likely some kind of central ionizing source. They said Pulsar nebula. I want to agree, but there hasn't been that much theory work done on it. The closest is this paper, Jerkstrand et al. 2017. And you can see their model here, the red one that they tried to fit to supernova 2015 BN at about 1 year post-explosion. You can see that this oxygen line as well. It fits fairly well, but again, this is just 1 year post-explosion. We have nothing that goes into the very, very late phase. And so if we can do radiation transfer, we can look at this kind of superluminous supernova, GRB supernova, and just regular type 1B, 1C supernova, and try and predict when we could see these forbidden ionization lines. And the other thing was the polarization study. So with polarization, you can probe the shape of the ejecta. And of course, if you have a central engine that's emitting non-spherically, it can distort the ejecta, and then we can start to see some of this distortion in polarization signals. And so supernova 2015, again, BN again, very popular supernova for observers. You can see that pre-peak, the photosphere or the ejecta, close to the photosphere and a bit further away, is expected to be of a similar geometry. But post-peak, we see that it gets much more distorted. And so this could be via energy emission or engine energy emission. And for 2017 EGM, we get kind of the same thing, not quite as drastic, but we go from axial ratio. This is axial ratio, if I didn't explain. From at the outside, it's 0.95, and the inside is 0.85. And this is done. This observation is done at about 6 months post-explosion. So we have some evidence for something at the center distorting the emission, but we don't know if it's just a normal dipolar pulsar nebula, or maybe it's something similar to a GRB jet that's not breaking out of the supernova. You would expect that, naively at least, that GRB jet would produce a much more distorted ejecta than just a pulsar nebula, but some simple, I think, hydro simulations would be enough to look at this problem and say how luminous are these engines to get this kind of geometry? What kind of shape does the emission have? Questions like this, I think, are still open, and there's really been no work on the theory side for this whatsoever. So these are two things that I'm looking at doing maybe during a postdoc. So overall summary for everything. Radio and millimeter predictions seemed promising. We should have seen, 5 to 10 supernova from the sample that we looked at, but we only got one detection. And so likely something is wrong with the specifics of the model. Most likely it's the injection spectrum. but there's still some work that we need to do on that. Infrared may be promising for close sources, less than 1 gigaparsec, but again, this really highly depends on the pulsar nebula spectrum. If they're crab-like, which we will probably see in radio 1 millimeter, then we wouldn't see them in infrared. But if they're non-crab-like, then we should be able to see them in infrared. Optical, late-time spectroscopy, polarization studies, these have produced interesting results observationally, but more theory work is needed. And my kind of long-term goal is to combine all of these diagnostics into like one sample. So if you see some interesting, superluminous supernova or GRB supernova on close, then we can look at it in X-ray, look at it in radio, look at it in infrared, do spectral polarimetry, do spectroscopy, and just get all these diagnostics for a possible pulsar. And I think we can learn so much about these systems if we can get all of these things working together. So that's eventually where I want to take this. And with that, thank you all for listening.
Thank you. I guess I've been asking most of the questions. Before I keep asking even more, does anyone else have questions? Okay, let me start first then. Somebody else can just let me know. So in the radio, if you looked, if there is polarization in the radio, is there?
I don't know if we looked for it. That would also be evidence for pulsar nebula, but I'm sorry, I actually don't remember if we even looked for it.
Because you would think if something is elongated, then even in the radio you could get synchrotron emission is polarized. Of course, if it's round, it cancels.
Yeah.
But if it's not round.
Yeah. The fact that I don't remember this means that we probably didn't look for it. So I'm sorry to say I don't remember, but.
And also in the radio, it seemed to me that this is kind of at the limit where VLBI might be able to even resolve this pulsar wind nebula. Is that right?
I forget what their resolution is.
So it's of order milliarc second at a few gigahertz, which
that might.
This thing is like, about a few thousand AU in size.
Yeah, that might actually be a really, really interesting measurement. And if we can do it with PTF10 HDI, a source that we know we have, then yeah, that would be
exactly.
Yeah, that would be amazing if we get it.
And is there expectation? Does the emission, it seems to me in this picture, comes kind of from the same place at all frequencies, or is the emission region spatially displaced? I mean, is it a bigger region at what? At lower frequencies, right? Because it's absorbed. The inside stuff presumably gets if synchrotron self-absorption dominates, then you have to go further out at low frequencies to see it.
Right. If it escapes the supernova ejecta at all.
Yes, that's right. But even when it does escape, it has to. You would be seeing it from further out than the higher frequency ones.
That makes sense.
I would think so. So with VLBI, I think the expectation, you have an additional prediction here about how big the object is at different frequencies.
Yeah, that makes sense. Yeah, I never even thought about doing VLBI on these, but yeah, I would have to look at what the predicted size is and if it's reasonable for VLBI.
Yeah, I mean, I'd be curious, obviously, since that's another smoking gun. Since this actually predicts a size that you could measure.
Yeah. I mean, if we can see it like with that resolution, we can learn so much. Okay.
So a lot of these figures you were showing had spin periods associated with them that were quite short, like 1 millisecond or 2 milliseconds. I just wondered what the motivation for that was.
So in order to get rotational energy out of enough rotational energy to power a superluminous supernova, you need to have a spin period of less than, I think the equivalence point between normal supernova kinetic energy and pulsar wind nebula or pulsar spin down energy would be about 5 milliseconds. So if you're going over 5 milliseconds, then you would expect it to just be as luminous as a normal pulsar or a normal supernova. So this is why you need these extremely rapidly rotating magnetars.
So this would imply there's some formation scenario that we don't understand yet.
Correct. Correct. We have no idea how to make these millisecond magnetars.
Of course, these are these rare, I think there's 1 in 1,000 or 1 in 10,000 supernovas that would be attributable to this rare channel.
Yeah. And there are some, I remember some studies of people who are doing, what's the magnetorotational instability, trying to find some kind of dynamo effect to get these extremely rapidly rotating magnetars. But so yeah, progress is underway, but I don't know for sure.
And just to see, in your particular case, is you're calling just a magnetar because you need a big field, not because it has any, not because of field decay matters.
Correct. I mean, this is powered by spin down, so technically, I think magnetar is the incorrect word. I even call it pulsar driven in the title of the talk. But yeah, it's a extremely highly magnetized pulsar.
Right, because you need some rapid spin down.
Yeah. But if you say millisecond pulsar, then it gets people confused. So we say millisecond magnetar.
Yes, no, it makes sense.
Okay. Other questions?
Well, if not, then thank you for giving a stimulating. I certainly thought this was